Hi everybody, welcome to the second lecture of algorithmic analysis. In the previous lecture, we discussed what's an algorithm as well as the differences between an algorithm and a program. We also discussed multiple ways of solving a problem as well as the benefits of evaluating an algorithm. We touched upon how can we evaluate different programs, and we discussed two different approaches. The first one was simulation or timing, where you basically used a stopwatch or a particular clock in C++ to decide if one program is running faster than the other. The second approach we used was modeling, where we basically counted the number of steps or of execution of two different programs. Finally, we concluded the lecture by stating there is a third approach which is more mathematically abstract in nature, which is the asymptotic behavior or order of growth of algorithms. We are going to discuss this order of growth of functions in this lecture, which is the asymptotic behavior or the asymptotic analysis. And we'll touch upon like why is that necessary, as well as how we do it, as well as the properties that allow us to analyze programs using this third approach. So the third approach, which is asymptotic analysis, came out of the limitations of the second approach. So I'm going to discuss a few limitations we discussed in the previous lecture, which was basically we had a program to count all the numbers from 0 to n and basically sum the numbers from 0 to n minus 1. We use the symbolic count method of modeling to count the number of steps, which is shown in this table. The issues with this approach was one of the most important issues with this approach was this can get like really complex, especially when we have very long programs, which is right now we could count that this particular operation took n plus 1 steps, but what if this entire loop was enclosed in another loop, and then these two loops are also enclosed in another loop? In such a case, it gets very tricky because maybe the first loop runs till p, the second runs till q, and the third one is running till n. So we would get like complex equations that could be something like mq uh, r minus 1 dot n and so on. So the few limitations with this approach was there are many different variables that could be across the program, and for large softwares this get very complicated. Another difficulty was that there would be so many different operations, which is like each of these are operation, and a software could have like millions of lines of code. How would we evaluate that, or even if we are writing a standard algorithm throughout the course, as we'll see in lectures of the last few weeks. Typically, all algorithms have about 100 to 150 lines of code, and all the symbolic counts get really messy. So that raises a question, can we eliminate the complexity or get rid of some of these extraneous variables? And what I mean by these extraneous variables or useless variables is like in this particular example, you can see that we are counting either each of the statements which have some certain value, which is here the int sum has value 1, while I is less than n has value like n plus 1. So when we are discussing like programs, the value that is assigned directly upon input heavily weighs the program performance. That is actually the gist of today's lecture, which is everything is dependent on variables rather than constants, which is like let's say if the total time of execution by the method 2 or approach 2 was 3n plus 4, and n was a number which was like 100 million. In this case, what would be the total time complexity of the program? It would be something like, what would be the total time of execution of the program? It would be something around 300,000 plus 4. So we can say that this 4 is so less or so minuscule that we can ignore all these lower order terms. And that gave a rise to this third approach that we are going to discuss today, which is asymptotic analysis. And this, to visualize why this can be a possible alternative, I have a list of these functions where y, which is actually just t of n, or the t of n that was borrowed from here, I have plotted different functions on the the first row of this header. The first column is basically the inputs, which is the size of the input. So, which is basically the values that could be possible for n. Now, when you're writing complex programs, you will understand why we have like these functions like n square, n log n, and we are going to discuss this again like in the next video where we discuss big O analysis. But the gist of it is, like, let's say if instead of this one for loop, there were two for loops, j0, j is less than n, and then j plus plus. In that case, basically this I is less than n, or the sum plus equal to I, this particular statement would not run till n, but instead would run till n square. And how you can visualize that, we are going to see an example very soon, but the gist of it is, like, if there are two loops inside one within another, you basically get a form of a rectangular execution where the outer loop runs till length uh, of the till the invariant of the condition of the outer loop, which is I is less than n, and the width of the rectangle is basically the number of columns. So in this case, what we got out of this entire execution is that, like, let's say if the time taken by a particular program, or the number of steps that are in a particular program, uh, can be different functions. Like there's this function is like one, where an example of this could be like int x equal to 0. A statement like this belongs to a constant function. Like if we have a int main and we just have int x equal to 0, we know that there's just one statement in the program, there's no input. So even if we increase the size of the inputs, we'll always get output equal to 1. And whenever we plot this graph, this would something look like something constant, either like this way or this way. So basically, if we plot the input n on the x-axis, which we did in the last lecture, and time on the y-axis, now input is increasing, but the time is remaining constant. So basically, the graph would look something like this, because the time is always 1, but the numbers are increasing. Similarly, for the next function, which is log n, this kind of case you can see when a loop is basically increasing from 0 to n, but basically we are updating the loop by the value 2 at every iteration, which is I equal to I plus 2. We are going to see some examples here, like of log n when those steps are calculated. But basically, what I mean by this chart is that the values of this function log n, if we pass in some values that are inputted to this function, which is n is from 1 to, in this case, 100 million. So in that case, the logarithmic function grows like this, which is it is nearly of the same order. But if it is a linear function, which is n, this grows linearly. And if you have n log n, you basically multiply these two, and then you have n square, where you basically square this particular values. And I plotted all this table in a normal Excel file. So what I saw was, if we increase the number of polynomials, like these are all polynomials because, sorry, these two are polynomials because we have n to the power some x value, which can run from 2 to any number. So the polynomials increase the input size uh, more faster compared to a linear function. And this behavior is even faster for exponentials, which is these are called exponentials. So if you have a to the power x, which could be a is any particular constant, it could be 2, 3, 4, or 100 million to the power n. So in that case, it grows even more faster, which is like if you see the values here, you can see like we already reached a value of 1 billion when we have a size of 1,000. And then these values were not being populated in Excel because they were so large, and these were even like not even the Excel was not even able to compute these values. That's why you see that these values have some error in Excel. So the gist of it is that the order of growth matters a lot when functions are getting faster. And what I mean by that is, let's say if our complex equation instead of 3n plus 4 was something like 3n cubed plus n factorial plus 2n square, then the values of our function or the time taken by our function would be dependent on the larger functions, which is in this case n factorial becomes really large. So let's say if we talk about a function that has 100 inputs where n is 100, like let's call an array of size 100 that's being passed into a function, and let's say the time computed using the method 2 is equal to n factorial plus n cube plus n plus log n. So in that case, only the dominant term will make the total time prominent, which is in this case, this term, which is 9.33 e to the power 157, which is like 157 zeros after this term. It's a pretty big number. Like if you add 1 to it, you wouldn't even notice, or you wouldn't even notice like if you sum this number, which is, I'll just use another color, should use a better color. So if I use this value, and if I sum this with the a million, and then if I sum this with n, which is in this case 100, and then finally if I sum this with log n, we'll see that the numbers, the function is, the time of the function is totally dependent on a larger function, which is n factorial, because it's growing much faster than another function which is either linear or polynomial. And this gives rise to something called asymptotic analysis, because what we got out of this is the function that grows faster truly determines the time of the algorithm. So in this case, we can eliminate the functions that grow slower. That's the entire gist of all that math that you just saw around. We are not going to go into too much details into the math behind it, but I would still show you a couple of different formulas, as well as I'll show you the definition of big O, because those are important. I won't be asking you a lot of questions on the math in exam, but it's always good to know some of those definitions. But if you want to go into depth into like how the proofs work, or like how do asymptotics work, you can always take the grad level course. So this brings up to the third approach, which is asymptotic behavior, which is the order of growth. And again, like what is order of growth? We are basically eliminating all the functions that are growing slower, which is in this case, let's say if this was a linear function, which is n, and this was a polynomial like n cube, we know that this is growing very fast and n is growing very slow, and this will never meet, or there's no possibility that n cube can overtake n in a future place, because n cube is growing exponentially. So if you see at a particular value, while tn might be for this n cube graph, Tn might be something like 100 here. The Tn for n at the same particular index might be much less. It could be just like 10. So that's why only the bigger growth rate functions actually matter. And we are going to discuss a formal definition of big O and these different notations very soon. But the third approach is basically eliminating all the lower order terms, which is when we are counting, we just care about the input to the function and we only care about the large inputs. And asymptotics is basically a branch of mathematics that basically deal with large inputs. So let's say if we have this function n cubed plus n square plus n, and if you have all taken a calculus course, basically you are taking this an integral of this function from 0 to x and assigning the limit x tends to infinity, we basically will get the higher order term in the end. Like you can see the mathematics behind it, but I'm not going into the detail for it. But the key idea behind this is the fact that asymptotics usually is a state of is a mathematical tool that allows you to compute functions for very large inputs, which is there might be some line or a function that grows asymptotically adjacent to another function, and they never meet to each other, but they probably go run parallel for a very long time frame. And why we care about large inputs is because we are all computer scientists. So what we need to do is we are caring about like large data sets. Let's say if you are making our social network, nobody cares like if a social network has 100 uh, users. If there are 100 users, you can use any data structure or algorithm, it should work fine. But it is truly the difference that matters when the input is really large, which is uh, in the previous set of videos we discussed, like Google is analyzing trillions of web pages or large amounts of data. That's when this asymptotic analysis or these big numbers try to make a lot of difference because the function grows very fast compared to some other functions. So we truly care about scalable algorithms. And the whole in the whole course we are going to discuss how we can use like asymptotic analysis, which we are going to discuss very soon, or the tools that or more mathematically rigorous tools to easily comprehend how much time is our program taking to execute. So that brings us to the notations that are adopted from asymptotic analysis. So there are multiple ways or notations or mathematical tools that we can adopt to understand the runtime or the space of our program, how much time or how much space is it taking. We are going to discuss three of them in our course. They are much more than this. Like there's big O, big omega, big theta, and then there's little o, little theta, and there are other, uh, sorry, little omega and little o, and other tools that can be used to analyze the runtime of algorithms. But we are going to discuss just three of them throughout this course. And after this lecture we'll just focus after the course we this lecture in the entire course we'll just focus on one of them, which is big O, and I'm going to give you a reason why we focus on big O. So basically big O gives us an upper bound or a maximum time on how much an algorithm will take to execute, while big omega gives us a lower bound, which is the minimum number of times minimum threshold of time that the algorithm will take to execute. And this big theta is basically, it provides us both an upper bound and lower bound, which is this program cannot work in less than this time and it cannot take more than this time. I'm going to go into a more mathematically rigorous definition in the next video, and we are going to discuss the various properties of these three different mathematical notations.